All right, that's not terrible.
Okay, so guys, one more X to put up here. Maybe we should make this a check mark instead, so I don't feel bad. Check. Check. Okay, so those averages that are on yours you had to compare, those were correct. Those were the actual population averages. I really want this to make sense. Every group made their own confidence interval. Any of these two confidence intervals the same? No, but they all come from the same data. So what's the probability that any confidence interval that's made won't catch the mean? What was the percentage confidence everybody had in their intervals? So what's the probability that an interval won't catch the mean? 10% chance. There were, 15 groups. So on average, I would expect 10% of 15, 1.5, on average, groups to not catch the mean. Are you guys with me so far? This is all that probability can mean is in the long run what's going to happen. So any specific, it's like flipping a coin is a 50% chance it's a heads. What the shit does that mean on one flip? Nothing, right? So that 90% confidence only comes into play when you have a lot of intervals. So I would expect about 10% of them around to not contain it. How many ended up? 1.5 on average. So maybe round up to 2. And we got 1, 2, 3 that did not contain. So that's about what we expect. You guys semi with me here. That's what that confidence interval level really means. Is that if I make a bunch of confidence intervals from the same data, I'd expect, if I'm making a 90% one, I expect about 10% of them to not catch the real mean. Maybe. I love this because this is concrete. You guys can see it. And it's always risky for me because one year I had every one of them caught the real mean. Oh well, but it's only 15. Right? So I expect 1.5 and I get none of them. That's still within the realm of what I expected. Okay, maybe. Yes?
Isn't the first one, didn't it catch the means? It was 81.22.
Oh, was that? Oh, did I get it confused with the females? I probably did. The men was 81.22. That's in there. Why? The females were 79.47. That's what I had over here. That one didn't catch it. And this one, yeah, so that's even better. Holy shit. Thank you. So now it's almost exactly what I expect. That's almost too great to believe. I think part of my brain was like, that couldn't have happened. Maybe. You guys feel a little better about T-scores? You guys remember 1-bar stats is going to be on the test. I'm going to give you a list of data and you have to come up with your own S. Okay, all right. The crowd doesn't give me any idea. Say again? Yeah, just like you did right now. You put it in the list and you do 1-bar stats. Yeah.
How do you do the 1-bar stats when it says frequency? What do you put that as?
Nothing. Frequency would be if it was an X and a P of X. The P of X column would be the frequency column. If you just put one thing of data in, you make the frequency blank. Yeah. What's their frequency, Kenneth? None.
Okay. So, leaving that behind for now. And remembering what's happening tomorrow. Quiz tomorrow. Cool. On what? Chapter 8. I like it. All right, cool. I'm always curious if anyone's going to be like, is he asking me to make my own quiz? No. It's going to be Chapter 8. Today we're going to get into Chapter 9. Which is, confidence intervals are good preliminary quick things to do. They're really quick to set up. So they could point out where things could be different. Are any of these confidence intervals not overlapping? Probably. I don't know. Let's see. Yeah, it looks like all of them overlap. Yeah. You guys see what I'm saying? Don't all of these intervals and these intervals, they all overlap, it looks like. So from what we've done, we haven't shown evidence that the population means are different between men and women, when in fact we know that they are. One is 79.47, the other is 81.22. So just like in real life, you will often get an answer that isn't actually true, but there's that in probability, there's always that percent chance you're wrong anyway. You could have done all the work right. These people did all the work right. We normally don't even know what the population mean is. I just happen to know it so I could see who didn't catch it. So when you do a confidence interval, there's a really good chance the real mean or whatever it is not even in there, depending on how confident you made it. Okay, maybe. All right. So today, we're going to develop something whose sole job is to test claims. So, let's see. Somebody help me out. Say I have a mean of 80 and a standard deviation of 6. I don't want to say this. So here's 80. If I go up a few steps, so if I took one test at random, just picked a test at random, and it came out to be 99, was that something I expected to happen? No, because it's like more than 3 steps up, right? So the same kind of reasoning applies with samples. If I take a sample and it's really far away from the sample average, so the whole thing about if something's unusual or not deals with how far away it is. I've been trying to set that up for the longest time. What does the z-square tell you? The distance from the mean to the data point in standard deviations, right? It's all about distance. Once I'm more than 2 steps away, then it starts to be possibly considered unusual. And even less than that sometimes in some situations, like the nuclear power plant thing. I want to get off my ass. My z-score's 1.2. I'm like, whoa, shit, it's getting close to yellow. Okay, so let's say that there's a lumberyard. There's a lumberyard that makes a claim. They say we can cut the wood to a length of, and they do all this stuff by hand. They don't have any, these poor people. They can cut their wood to a mean of 42 inches. And I want to test their claim. I want to see, okay, how good are these people really? They're doing all this by hand. Let me check it out. So I take a sample of 50 pieces of wood from this lumberyard, and I get a sample mean of 40 inches. And now this should be, by itself, is that evidence that they're wrong? Not really, because I could have just happened to pick a bunch of boards that were smaller. Maybe if I took a larger sample, I took another sample, maybe it would come out to be this, or maybe even higher. So it's all about, is it far enough away from this to show that their claimed average is wrong? That's the whole thing. Any sample I take can be away from the real mean. So it doesn't just have to be different, it has to be different enough. One big thing about these tests we're going to do in Chapter 9 is establishing what far enough away is. What am I missing to really start looking at this statistically? There's one thing I'm missing. There's the underpinning of what the real idea is. Standard deviation, because the whole thing is based on how far away things are. Standard deviation tells me how to measure distance. So if I found that S was, I don't know, 0.5 inches, are these very far apart? In fact, how far apart exactly? What would the z-score be? It'd be 2 divided by half, which is 2 times 2, 4. So it'd be a z-score of 4. That's a negative 4 in this case, right? Because it's below, but still, it's like 4 steps away. That's evidence that they're wrong. But what if S was 2 inches? Now how far away is this? Yeah, so I like it. Maybe. Okay, so so what we're going to do is, the way they do chapter 9 of the book is we're going to end up with 5 steps to what's called a hypothesis test. The book has a worksheet in the back that they ask you to use. Screw that worksheet. You're going to do the steps I give you. When I took this, it was 8 steps when I learned it. And I whittled it down to 5. You're welcome. What the book does in chapter 9 is it kind of takes each step and puts it in its own section, which is really frustrating, to be honest, but oh well. So I'm going to go through an entire problem with you, trying to set up what these steps are going to be. Okay, so let's say, I wonder if I want to do that. Maybe I should, yeah. Here, instead of me trying to make something up, I've got this. I'm going to go through this together.
Professor?
Yes.
So the scientists use this? Is that why they came up with the name? To like
Well, it's
further their hypothesis?
somebody makes a claim that must be based on some kind of data they have or some kind of evidence they found. So that's a hypothesis. They make a hypothesis, and then we're going to test it. So anybody uses this that wants to. So you know there's scientific journals, physics journals, and statistics journals, business journals.
Yeah.
But where does statistics apply? What can statistics be used for? Every damn thing in existence. So, who uses this? Everybody that's trying to say something must use this. These are already too far ahead here. Let's. Oh shit! I gotta rearrange my camera now. Let's see if I can make this work. Are you still recording? Yes. Yay. Okay. Can you do the... Thanks, man. All right. So, what should be really obvious is the very first step has got to involve what the claim that's being made. And what we do is... So read through this. Let's see if you guys... What's the claim that's being made?
That coyotes live longer.
Everybody has one of these, right? Did I give everybody? No, looking at me. You should be reading this. What's the claim that's being made?
That coyotes live longer in captivity than anyone.
I like it. Now, make that much more mathematical. There should be some numbers and some symbols. So Phil claims that the northern Minnesota coyote, that means all freaking northern Minnesota coyotes, live longer in captivity than they do in the wild. So how long do they live in the wild? So what does he think then? He thinks the average lifespan of Minnesota coyotes, what symbol do I use? Say again? No, I mean, what symbol do you use for the average age of all Minnesota? The mu. He's claiming that the mu for these little coyotes is greater than, you can do it? 7.25. Now notice, what's this 8.65 that comes up later in the problem? What is that? That's the sample average. I would never make a claim about the sample average because I can frickin' see the sample average, right? That'd be kind of dumb. I claim that there's 5 fingers on this hand. Well, Jeff, you're right. I mean, so I'm not going to make a claim about something I can see. I'm always going to make a claim about some known number. The sample information is never going to show up in the claim. That wouldn't make any sense. Maybe. Are you guys cool with that? I mean, you calculate the sample. Why would you make a claim about the thing you just calculated? It's right there. You wouldn't make a claim about it. Now, here's where things get
Interesting. If that's the claim, there must be something this claim is fighting against. So if I'm like, I claim that the store marked their prices up, what's the store's stance? No, either they didn't or they made it go down, even. Just the opposite of what I just said, right? Otherwise, there'd be no dispute, there'd be no reason for a test, everybody's in agreement, let's just all go home, right? So if he's claiming this, there must be an opposite stance. That only makes sense. That's these guys. I always think about these guys as two old men in a coffee shop. You've seen these people, right? And they're always kind of arguing or whatever, possibly. And they have completely opposite opinions very often. Right. The way we've set this up, it's just the way we've set this up. The high, H1, I call it the high,
Okay.
is always going to be the thing that I can show evidence for. Now let me ask you this. You guys just stay with me, please. Hold on. If I take a sample, if I took you guys and I got an average age, let's say the average age here is 24. Does that show evidence that the average age for everybody is 24? No, because, I mean, any sample is going to have an average difference. So I can never prove or show evidence that something equals something. But if I took an average age of these, let's say these 3 rows, a little bit bigger sample, and their average age is 24, is that evidence that the average age for everybody is less than 26? Yeah, it could be. Right? If they had an average of 24, that is less than 26, it might be evidence that it's less than. I can take a sample and show evidence, just like we did with confidence intervals, that something isn't something. But with a sample, I can never prove that something is something. You guys kind of get that? I can never prove through a sample that the average is 8 of something. There's no way in hell, because every sample is going to be a little different. But if I take a decent sample and the average is 8, that might be evidence that it's less than 10. So this statement, the claim that's being made right now, is it something I could show evidence for? In fact, what did he find? It's 8.65 years, the sample he took. Now, that could be evidence that it's greater than this, right? You guys with me? But for example, is that evidence that the average is actually 8.65? Because again, samples can be all over the freaking place. But a sample, especially 41 is a decent sized sample, could be evidence that it's different somehow. That is why this one is the one that does not have an equal sign. This one is the one that does. This is the one that I can show evidence for. And this is the opposite. So if my claim has an equal sign, I'm going to put it down in yes, the hoe, right? The null hypothesis is the technical way to say this. So you got the hoes and the highs. So if this had an equal sign, I would put it here. It doesn't, so I'm going to put it here. This is going to be the old man in the coffee shop that thinks this. I kind of like that old man in the coffee shop. So I'm going to put, since this does not have an equal sign, that's all there is to it. It doesn't have an equal sign. I can show evidence for it. I'm going to put it next to H1. So what's going to go in the hoe? What's going to go in place for null hypothesis?
Less than.
Yeah, what's the opposite of greater than? Nope. Less than or equal to. So what must be in the statement next to the null hypothesis, the hoe? It's got to have an equal sign. It's going to be the thing that I can't show evidence for. The H1. So if my claim would have been, I think it equals 7.25, I would have put that next to HO. That's it. So if you write the claim down and it's got an equal sign in it, you put it next to HO. If it doesn't, you put it next to H1. That simple. We just set it up that way so we can always attack these things the same way.
When your claim has an equal sign, you put it next to the HO.
Beautiful.
What would you put in the H1?
The opposite. What's really funny is you write the claim down and then you figure out which one to put it in, and then whatever that is, you put
but the opposite in the other one.
So would you put not equals to?
Yeah, exactly. I love it. Sweet. How are we doing so far? I know this is this step is very different from anything we've done before, but it's not that horrible. If you can write what the claim is in math, you can figure out where to put it, and the other one's the opposite. Maybe. Now, what's your gut say? Yeah.
I was gonna ask, isn't he claiming that they live 8.65 years in California?
No, he's not. He isn't. In fact, when do I make a claim about something? Before I even take a sample. Does that make sense? I'm going to go, I think this. Let me go take a sample and see if I'm right. So that 8.65 number doesn't show up anywhere until step D, when we actually want to see how far that is. Maybe. And it wouldn't be explained because he knows that's the sample mean. Right? Okay, let me see. Blah, blah, blah. Now, what's your gut say about how many tail tests this is? Which statement can I show evidence for? Which statement can I show evidence for? The high. I can always show evidence for the 8 shy. Or fail to show evidence for the high. And this is the one that says it thinks the mean is greater than this. So how many tail tests do you think this is? What's your gut tell you? How can I show that something's greater than that? I have to show that my sample is above it. So it's just a one-tail test. I've got to actually show that it's above. So here's the idea. So again, what's the whole thing? Why can't I just stop right now? I used to have people that are like, "Oh shit, that's bigger than that." Just flip and move on with your life. But no, why can't I do that? Because this is just from a sample, and a sample's always going to be different. The whole idea is that number different enough to show evidence, right? Yes, no? So somebody's like, I'm psychic. I can tell like how old somebody is just by reading their mind, right? And I'm like, I think you're wrong. And they say, this person's 38 and they're 39. That's not evidence they're wrong. But if they say, this person's 38 and they're 60, that's evidence that they're wrong. You with me? Why was the second one evidence they're wrong? Because they're really freaking far off. So, it is a one-tail test, because where must the sample show up to show evidence for this? Here's the 7.25. The sample would have to show up way up here somewhere to show evidence that it's greater. Not just a little bit bigger, it's got to be a lot bigger. In the third step, we're going to define how far away that is. In the past, it used to always be 2 steps away. That's where unusual started. Now it's going to be a little more nuanced. We can make it different for each problem. So what's the shortcut here? It was a one tail up there because that's where this thing points. If it was less than, it'd be down there. If it was not equal to, how many ways can it be not equal to? That would be a 2-tail test. Now you start to see why the t-score chart has 1 tail and 2 tails. It depends on which kind of test you're doing. Like it. You like it. Okay. Step B is going to be old news. Do you use z-scores, t-scores, or nothing? 2 things you got to check. What's the most important thing to check? Is it normal? Yeah. Is it?
Yes.
Why?
The sample size is over 30.
I love it. N is 41, which is bigger than 30. Check. And then what do I check now? That tells me I can do something. So the nothing option is off the table. So do I use Z or T? Which one?
Z.
Why Z?
Is the standard deviation?
Don't say because there's a standard deviation. There's always got to be a standard deviation. Population. I know sigma. So I can use z-scores. Right? Why were t-scores invented? For when I don't know sigma. When I only know s.
So if you didn't know what he took a sample of, then you'd use...
If I didn't know what sigma was. If that 3.27 came from his sample, if it was s, I'd have to use t-scores. But because it's the standard deviation for all northern Minnesota coyotes, it's sigma. So I can use a z-score. Of course, if you missed yesterday, you're like, what the shit? Okay, but it's too bad. You gotta watch the video. So let's see, sigma unknown. Or, yeah, sigma known. Sorry. Use z-scores. So what I always like to say is this is what the hell we're talking about. This is what we can use to talk about it. Here I got to say what's far enough away. Do you see that whole alpha is 0.01? And how many tail tests do we have? One tail test. So can you look on the t-score chart to give me the z-score for this? Where are z-scores on the t-score chart?
At the bottom.
So I got one tail, 0.01, all the way at the bottom, I get 2.326. Do you guys see that? One tail, 0.01, all the way at the bottom, 2.326.
Why is it all the way at the bottom?
You guys tell me, if I stop, I get what? If I stop, I get a t-score. If I go all the way to the bottom, I get a z-score. Why? When the sample is big enough, I don't need t-scores to save me anymore. I can just go ahead and use a z-score. Why are t-scores invented? So that they make it a little bigger to cover my ass for not knowing what sigma is. But if I have a really big ass sample, S and sigma are going to be the same. We're close enough. So then I can just use a z. That's why those are z-scores at the very bottom. Kicks a lot of ass. Because this chart is set up perfectly for hypothesis tests. So if I stop, I get a t-score. Go all the way to the bottom, I get a z-score. Is that simple? And you guys are like, you know what that word means? Simple. Okay. So that means I got 2.326. Why is it positive? This is up here. So be careful. I know all these are positive, but that's because we're humans. We know when it has to have a negative sign on it. In this case, it doesn't. So this is what's called the rejection region. So let me see you guys again. All right. So I really, Jeff, why'd you come over here? This is the region that HO thinks is true. HO thinks it's in here. HO thinks it's less than or equal to. So it thinks it's in here. To show that this is true, I have to get in here. Does that make sense? I have to be far enough away. So here's the 7.25. Here's the mean. If my sample is way over here, what could be true? There could be one thing. I could get something in here, couldn't I? There's actually a 1% chance I'll get a sample in here. 1% chance. If that's really where the mean is, there's a 1% chance I'll get a sample in here. So what's more likely? This isn't really where the mean is. For my captivity, the ones in captivity, the picture maybe has moved up a little bit. I really want this to make sense. So what we do with hypothesis tests, we say, assuming you're right, assuming the mean really is 7.25. And we get in here, we'll say, look what we just did, right? Look what we just did. Assuming you're right, look, I just got way the hell over in here. There's a 1% chance you're right now. So what's more likely? The HO is wrong. So if I get in here, what percentage of samples show up in here? 1% of samples. If this is the real middle, there's only should be 1% of the samples that show up in here. So if I randomly take a sample and it gets in here, there's a 1% chance I was going to do that if the mean is 7.25. So then what's more likely? The mean is bigger. That's what's more likely.
If you pull the 1%.
Huh?
If you pull from the 1%. The mean
No.
is bigger?
If I get in here, and that only had a 1% chance of happening, if that really is the middle, what's more likely? That really isn't the middle. The picture really looks more like this, maybe. So assuming the middle is 7.25, there's only a 1% chance I get in here. So if I get in here, there's a 1% chance I'm wrong if I say that that really isn't the mean. But holy shit, 1% chance I'm wrong? That's better than normal for me. So what's more likely is that really isn't the mean. The mean is bigger, and isn't that what H1 says? So that's why getting in here is evidence that H1 looks right. It's evidence that HO looks wrong. So we call it the rejection region, because if you get in here, get ready, you can reject the HO. The null hypothesis looks wrong. Because it's so freaking far away from what the null thinks that it looks evidence that it's wrong. Oh, you guys are loving it. Yes?
So I just want to make sure I understand. So if it's in the rejection region, then that means it's true.
Then I can reject the null, reject the HO, support the high. Sounds like some propositions that were on the last.
So if it's in the rejection region, then you reject the If it's in the rejection region.
Yeah, that's why we call it the rejection region. If I get in there, I reject the null hypothesis. I got so far away from what the null thinks that more than likely it's wrong. Is there a chance that I'm wrong? Oh, hell yeah, always. Statistics is very honest. It's like, there's always a chance you're wrong, dude. Holy shit. But it's really good evidence that we're right. It's only 1% chance we're wrong. That's pretty damn good. Okay. So how do I say this in words then? So let me make sure, let me see if you guys are cool with this so far. What is that 2.326? That's like my benchmark z-score. If I get a sample z-score bigger than that, then I'm going to reject the null. Does that make sense? That's the whole idea of what we just talked about. If my sample is further away than 2.326, that's evidence that the mean is in the wrong place for these coyotes in captivity. Okay, I like it. So see how 2.326 is a z-score already? So do you see in the next thing, I call the sample z-score z star, just to differentiate it. You guys are loving life right now. All right, if my sample z-score is bigger than freaking 2.326, what does that mean I can do? I can reject the HO. I love it. Somebody's like, I don't want to say HO. Support the high. Sounds like somebody might already do. Again, what's the whole idea of a hypothesis test? Here's where one dude thinks things are. We go find something that's so far away that that dude must be wrong. That's the idea of it. The steps get very detailed, but that's the whole idea. There's a benchmark. If we get past it, we've shown evidence that that dude is wrong. The HO is wrong. Which at the same time, now look, if I can say HO is wrong, that must mean I can support H1. I can't prove H1. Never. But I can support it. Like it. Alright, so this is what the hell we're talking about, what we're allowed to use to talk about it. What's far enough away? And how far away did we get? That makes sense. The very next step should be, well, how freaking far did we get? So what do we know from the sample? Somebody help me out. What's X bar? 8.65. And sigma, we know sigma, that's 3.27. And I give you a little hint here. I obviously have to do this. Why? Because we took a freaking sample. What's n? 41. So what's the new standard deviation for groups of 41? Anybody wants to help me out? 0.511?
Yes.
So now we can calculate, go ahead and calculate what the z-score is. I just call it z-star because it's the sample z-score.
get square root of 41 for the...
What was the sample size? Oh, cool. You guys get that z-score yet? Oh, yeah. Oh, dude, calm down. Shit. I get this. 2.74. Is that far enough away to reject the hope?
Yes.
So up here, what can you do? You put a little line with a star in it. That's our sample. That's another reason why I call it Z star. You put a little star in it. That's our sample. We got really far away from 7.25. If that was the real mean, any sample I take should be close to it. Right? Not every sample I take will be, but every sample I take should be. There's a 1% chance I would get a sample that was way out past 2.326. So what's more likely? That that's not really the mean. The mean is further up. That the picture, what's more likely is the picture looks like something like that, a little further up. The mean would be a little further up. So then our sample we took wouldn't have been so unusual. Really. This is really freaky, I know, but it's not that freaky. So hypothesis test is all about saying, all right, assuming the 7.25 is right, look what we just did. We just did something really unlikely. In fact, we can be a little more specific. Isn't that way further away than 2.326? Can somebody find the area in the tail that that z-score makes? Please. That's old news. You guys should be able to do it. What's the area in the tail of 2.74? The area here. Above the 2.74. Careful. That's the area in the body. 0.0035? Let me see.
Yeah.
Oh, I don't have my z-score
Yes,
picture.
3.
I gotta take your word for it. What is it?
3.
Here we go. All right, one eyeball and no lights. Let's see if I can do this. 2.74. 9969. So it should be 0.0031, right? Yeah.
That's what's called the p-value. So what's the real probability that I would have gotten something around where I did? About a 0.3% chance. 0.3% chance that we would get something where we did if the mean was in the right place. So what's more likely? The mean's in the wrong place. Should be higher. If somebody's like, I think everybody in this class is like 20, and then I talk to people and they're all 24, 25, 26, that's evidence that that dude is wrong. That's basically what just happened. Is there a chance we're wrong? That it really is 7.25? Of course there's a chance. A 0.3% chance. Yeah. I like it. Another way to look at this is, well, this gets a little freaky with the p-value. If you search for p-value, number one, you're my kind of person. I love it. Look at some videos about p-value. There are people that want to throw it out. That's foolish. The problem with p-value is people misinterpret it. Again, what does this mean? Does this mean that for damn sure the captivity makes Minnesota coyotes live longer? Is that what this means? Is that what this means? No. It's good evidence that there's a connection. Right? And why would that be true? Why does it make sense that they should live longer, possibly? There's all kinds of bad things about captivity, but what are they getting in captivity? They're getting separated from other things that would have killed them, getting regular meals, right? But then again, in captivity, you get, bad things that happen too, but this seems to point to they live longer in captivity. So, all right, you're going to love this. So just like with confidence intervals, you've got to write a conclusion. And here's how this conclusion is going to sound. So did we make it? Did we succeed? Yes. And what was our claim? Which one was our claim? Which one was our claim? Which one?
The high.
High. I like it. So we made it in here. We can say these things, can't we? But somebody made a claim. When I give them the answer, I probably should talk about their claim. So what language do I want to use? This language. Why? Because their claim was H1. Right? Alright. We're going to do some more examples, obviously. But the way you word your conclusion is based on which one was the claim. You're going to have to tell the dude what happened with the claim. So did we made it in there. So we have found sufficient evidence. To support the claim that, and then you just steal from the problem, that the northern Minnesota coyote lives longer in captivity. Don't just say we have shown evidence to support the H1. What the shit does that mean? Right? Some client hires us as statistical consultants, and we say we support H1. And what the hell does that mean? Give me some language that references what the problem is. Okay. So if I ask you how you feel right now and you're honest, you'll say, I don't know. I really don't. Let me see on the back here. Read through this problem. I want to try to let you get a little ahead of me on each step. Try to figure out what part A is. And then I'll catch up to you. We'll take a break when we're done with this problem.
This is like equal to.
I think so.
All right, let me catch up to you. Let's see. Oh, man, Jeff. Why are you doing this to yourself? I've hidden my pen somewhere. Here's a pen. Let's see if it works. Having a mostly blind teacher is not easy. Okay. Does this pen work? Yeah. Okay. All right. What's the claim? Who? Nope.
Mu equals 30.
Yeah. What they say? The Ford Focus modification is made, and now Ford believes the assembly time has changed. What's really weird about having all the information given to you at once is you lose information about the order of things. They make a claim before they take a sample. So don't go 37.3 is less than, no. What's the claim? Changed. So they say, what's changed mean? The mean is not equal to 38. That's the claim. So where does that go? HO or H1?
H1.
H1. It's got like the opposite of equals. Right? So then what's HO? No, wait. Okay. Because that's the opposite. So will this be a one-tail or a two-tail test? Two-tail. I like it. Does not equal 2 means it can be greater or less. The Lord, Jeff. 2. All right. Anybody thought about part B yet? Say again? T? Why T? Yeah, which standard deviation do we know? Good. Sigma unknown. What people do, they'll say, I know the standard deviation, so it's Z. That doesn't make any sense. The standard deviation, there's 2 types. Which type do you know? Sample. Now, what tells me I can do anything? Why is it normal? Yeah, N is 71, greater than 30, check. What if N was less than 30? What do you look for? Does it just say it's normal, right? That's going to happen too. They're known to be normal, sample is 7, and then you don't say, well, it's not big enough. No, I told you it's normal. I don't care what size the sample is. All right, try to do part C. Ah, sweet. Good.
Yeah. Yeah.
No. H1 always sets up the rejection region. Always. So how do I show something is not equal to something? They have to be really far away, either direction. Rejection region is always going to be out in the tails. Because that's the only way you can show evidence against something is if you're really far away.
So we got T-squared here, but how would you give a population?
The same way I did it on the front page. I'd just say it is known that the population standard deviation, or it's known that the standard deviation for all assembly times, I'd have to tell you directly it was a population standard deviation. This one just came from the sample, so.
So maybe was it the sample or
No, it's the 38. Because part D is where we actually take the sample, to be honest. So everything up to that point is based on the claim number. What we're claiming against or for. Yeah. Don't overthink it. How many tail tests? 2. 2 tail. And 1 alpha. Don't overthink it. Look at the T-square chart. How many tail tests? And 1 alpha. Bam. Don't overthink it. It's set up beautifully. You don't have to, do I cut this in half? No. Just whatever it is, and then you look at the right 1 or 2 tail, you're gold.
Thank you for the T-squared chart, please.
Did I lose my other predictors?
0.25.
So we got to use T-scores. Degrees of freedom here is 70. I like it. Alpha is 0.05. It's a 2-tail test. So don't overthink it. Don't think, do I cut that in half? No, strip. 2 tails, 0.05. Stop at 70. Kabam. That's why this chart's so beautiful. You don't have to think a lot. You just have to go to the right situation and get the number. So it looks like it's 1.994. Where do I put that on the picture? No. What would go in the middle? 0. That's the mean. It would be 0 when I translated it into t or z-squared. So what goes here? Negative 1 point, what was it, 994? Right? The positive 1.994. It's a two-tailed test. So this is where we step in. We go, that's a nice chart. You tell me 1.994. I know I've got to use negative and positive because I have a two-tailed situation. How are we doing so far? I mean, that's... Yes? We knew from the beginning. If H1, bless you, is not equal to, that's when it's going to be two-tailed. And what I like to say is, in the write-up, if you see a directional word, like we think it's increased, we think it's gone down, we think it's gone up, we think there's fewer, we think there's more, that's going to be one tail in whatever direction, right? If you don't see any of those words, then that's, because the two-tail can be hidden sometimes. The mean is 47, we think it's the same now, blah, blah. It's really easy to look that over and go, oh, shit. But it's the same. The opposite is not equal to. Two tails. I like it. All right, at least you guys are all looking this way. So this sets up my rejection region. How do I say this in words? If T star is, how do I get in here? If it's less than negative 1.994, or T star is greater than 1994, what can we do? Reject the hope, support the high. Sounds like possibly good luck. Tips. Yes.
Would you ever just say if the T star doesn't equal 1994, can we check that?
No. It's way too specific. What's the probability that I get exactly 1994? 0. That's a continuous thing. I can only talk about regions. So I can never say if T star equals something or doesn't equal something. That's impossible. I mean, it's either impossible or the only thing that can happen.